Alright, so in this video we're going to talk about Chapter 2 in STA 2023, Intro Statistics. Chapter 2 is all about descriptive statistics. Now we did some descriptive stats in Chapter 1 also. Remember what that is. Descriptive stats is just when you're making tables and charts or doing things like calculating summary measures. So we're going to continue to make a few different kinds of charts here in Chapter 2. But most of Chapter 2 is going to be, most of the time here is going to be spent doing things like calculating summary measures. So today we're going to do things like calculate quartiles and percentiles and talk about calculating means and things called standard deviations and calculating those. And we had two special words, statistics and parameters. So numerical measures that represent a population, that's a parameter, and then numerical calculations that represent a sample, that's a statistic. Remember, if you want, you should be following along with these notes, because this is the important stuff that you need to know. I mean, stuff out of the book, we skip some stuff out of the book, we add stuff that's not in the book. This is the stuff you need to know on these notes. So you can get these notes in Blackboard. There's a folder titled Guided Notes. Make sure to download them there. Also, there in that same folder, there is called a key formula sheet. This page right here, it's 2 pages actually. That's in the same folder, the Guided Notes folder. We will start to accumulate a pretty good number of formulas here in Chapter 2. There was a couple in Chapter 1 that we talked about, but not many. You do want to make sure to familiarize yourself with this formula sheet, because this is the formula sheet you're allowed on the test, and you want to know where all the formulas are and know how to navigate this quickly. So make sure you're using this when you're doing your homework, so you know, say, where to find the formula for standard deviation or for a quartile or percentile or whatever you're looking for. Okay, again, look for this in the Guided Notes folder. Okay. So let's see. On this first page or so, first page and a half, let's talk about a couple different types of graphs. The first is going to be a stem and leaf graph. Now, a stem and leaf plot, stem and leaf graph, also called a stem plot. There's not really it's kind of one of those weird things. It's hard to just say a definition for what it is. It's a way to display data, of course. But here's kind of some instructions about how to create a stem plot. Basically, you take each observation, so each test score, each weight, each whatever you're measuring. By the way, this is quantitative data. This is numbers, not qualitative data. Stem and leaf plots are with quantitative numerical data, and you divide each observations, each number, into what's called a stem and a leaf. The leaf consists of the last significant digit of the number, and the stem is the other portion. So remember, the significant digits, so basically if you're dealing with whole numbers, the significant digit is going to be the ones place. So let's take a look at an example. The following data consist of the scores of a prior stats class. Construct a stem and leaf plot for the data. Okay, so there's a bunch of test scores, and we want to make a stem and leaf plot with those test scores. So these are all 2-digit scores, of course. If your tests range possibly from 0 to 100, they're going to be 2 digits unless you make a score of 100. But here they're all 2-digit numbers, and the way you make a stem and leaf plot is you take all of the numbers. And first of all, write your stems in this first column. The stems are going to be all of the values in the tens places, because the leaves are all the ones digits. So it looks like we have, let's see, I don't know, where do they start? I see numbers in the 30s. Is that as low as they go? And I see numbers in the 90s. So I guess what I'm going to do is going to write 3, 4, 5, 6, 7, 8, 9. Okay? And then what we do here is that we go find, say for the 30s, all of the 30s numbers, all the numbers in the 30s. And what we do is we just write the leaves in a comma-separated list right here. Now, what are the leaves? Again, the leaves are the ones digits. So for 33, I would just write a 3 right there. That's the ones digit, comma. Let's see, cross that off so we don't count that again. And then go look for more 30s. Are there any more 30s? I guess not. I don't see any more 30s. So I guess we actually don't need a comma there since there's only one number in that list. Now I'll do the same thing for the 40s. Okay, I see a 42, so 2. Let's see some more. So comma 9. Oh, there's 2 49s. So we do have to put repeats there. So there's 2 49s, so I need to have 2 9s in my list. Let's see, any other 40s? I don't see any more 40s. Now, the point of this graph is, well, first of all, the point of any graph, I suppose, is just to be able to compactly represent your data, maybe be able to display your data so you can easily ascertain something about the data. So here, it's a way to organize the data, and what you'll see when we're done is a stem and leaf plot kind of helps you see where the bulk of the data are, kind of like a dot plot, except oriented the other way. Here, let me show you. I'll show you once I get done here. 50s. Okay, there's a 53. Okay, 53, and then 55, 55. So I'm going to do 3, 5, 5 like so. Let's see, any more 50s? Oh, I just realized I have these data ranked, so I don't have to keep. I was kind of going up and down like this, but clearly I have the data listed from least to greatest, row by row. So no, those are all the 50s. 60s, okay, there's a 1, a 3. I'm not sure why I didn't notice that. I made these notes. 3, 7, but it's been a while since I made them. 3, 7, okay, there's an 8 and 8. Remember, you have to include the repeats. Then a 9 and a 9. Okay. Now the 70s, there's a 2, 72, 3, so a 2, comma 3. 4, 8. 4, 8, okay, that's that. 80, so 0, then comma 3. And then 8, 8, okay, there's 3 8s. And then 90s, okay, there's a 0. Then there's a 2, 4, 0, 2, 4, 4, 4, 4. So 3 4s in all, and then a 6. Okay? Now, by the way, that's actually, since I had the data ranked over here, ranked just means least to greatest. Or I suppose it could be greatest to least, but usually we mean least to greatest. So it happened to be that when I wasn't trying to at first, but then I realized halfway through making this that the data were ranked, and so my leaves were also ranked. So I guess this would actually technically be a ranked stem and leaf plot. However, a stem and leaf plot in general does not have to be ranked. By ranked, we just mean that the leaves are ranked. The leaves are listed from least to greatest. But for a regular stem and leaf plot, that would not be necessary. There would be nothing wrong if I wrote, say, that list of numbers as 6, 2, 4, 0, 4, 4. Completely out of order. Wouldn't make a difference. But if you're asked to do a ranked and stem and leaf plot, all that means is that you need to have your leaves in ascending order. So a stem and leaf plot, again, what we can see there is that clearly just by glancing down, you can see that most of the data are in the 60s. Then you have 90s, 80s, 70s. There's 3 observations each in the 40s and 50s, and there's only 1 observation in the 30s. So this allows you to glance really fast and see where most of your data are. Also, kind of like a dot plot, think about If you turn it like this, where the graph is taller, that's where most of your data are. So again, just because the list is longer, because there is more values there, that results in there being taller bars here. So it's kind of like the same thing as a dot plot, except we're oriented horizontally. So where the longer list is, that's just where more of the data are. Okay? Where the list is shorter, that's where a lesser amount of data are. Okay, so that's a stem and leaf plot. Again, technically that's how I have it written here is a ranked stem and leaf plot, since the leaves are in order. Now, what about outliers? An outlier, also called an extreme value, is an observation, so a datum, a data value, that does not fit the rest of the data. So it could be a lot larger or a lot smaller than the rest of the data. Okay? Now, there's different ways. We'll see a way in just a little while, kind of a method to mathematically quantify a outlier. There's different ways to calculate. Yes, this is an outlier, or no, that's not an outlier. We're not really worried about that at the moment. But just think about a data value, an observation that's unlike the rest. For instance, it seems like somebody always skips a test. You know, whether a student who just say stopped coming to class or something like that. So, I give a test, and let's say that most everybody makes A's, B's, C's, D's, and maybe there's a couple F's, but maybe like they're in the 50s or something like that. But then if somebody doesn't take the test, they get a 0. Well, obviously 0 would be an outlier, because if you have a bunch of all the test scores for the entire class are, say, in the 60s, 70s, 80s, and 90s, and maybe a couple 50s, but then you have a 0, well, that's way outside the distribution of the typical scores. Okay, so an outlier usually indicates something weird happened. Well, in this case, somebody skipped the test, so that is something weird happening. Okay, so outliers aren't necessarily, there's anything wrong with them, but they sometimes indicate that just something funny is going on. Okay, so they're always worth giving a second thought to. All right. What about a line graph? A line graph is typically used to show how a variable changes over time. Data points are connected with line segments. The thing is, with a lot of these charts, computers are really great at making nice, fancy charts. Basically, I want you to know how to read these charts, what they mean. Okay? Because it's kind of, we're going to make one here, but it's kind of, not a very efficient way to do these by hand, I guess. Because a computer can make this and do it perfectly. Ours is never going to be perfect. It's going to be just a rough approximation. So I want you to understand what a line graph does and what's the purpose of a line graph, and how to make one generally. But I'm not going to ask you, like on a test, to make a line graph. It would be more like things like maybe choose the correct one, or say read the line graph and what is it telling you, that kind of stuff. All right, so notice what's happening here. We have a restaurant server records his weekly earnings over a 6-week period, as shown in the table over here. Construct a line graph. So yeah, we have the earnings are measured in hundreds of dollars, and the earnings from week 1, 2, 3. So this is how his earnings went up or down over time. And so to make a line graph, basically we just treat these like the x values. So I would label this axis down here, the week. 1, 2, 3, 4, 5, 6. And then here, this would be dollars, well, hundreds of dollars technically. So dollars, measured in hundreds of dollars, something like that. Okay? So the first dot we would do, basically, if you think about algebra class, 1, 6. So 1 on the x-axis, 6 on the y-axis, so something like that. And then week 2 was 8, so 2 on the x-axis and 8, something like that. Week 3 was $400. So maybe somewhere about like that. Then week 4 was 300. Okay, so that's down even a little bit lower, maybe about right there. Then week 5 was back to 800, so 5 on the x-axis, and back up here to that same height. Again, we can't be absolutely perfect here. We're just doing a rough approximation. And then week 6 made $1,000, so that's a 10. So above 6, we're going all the way up to the top. Yeah, something like that. And then with the line graph, what you do is you just connect with line segments. Okay, so it shows how the variable, in this case, the variable is weekly earnings for a server, how they're changing over time. And so again, always think about that a graph or a chart, the whole point of such a display is to allow the reader to quickly gain information about the data set. So here we can clearly see that, he had a little spike here in week 2, then there was a couple slow weeks, and then towards the end of the time period, the last couple weeks, the earnings went up. Okay, so you can see the trend of going up briefly, then down, then up. Especially if you did this for over many weeks, you could see a nice graphical depiction of the money earned over time. Think about like a stock market. If you look up say how the S&P did over the past year or the past day or whatever, you're going to see this exact same kind of thing. Okay. If you look up daily stock prices you're going to see all kinds of line graphs when you look at financial data. Okay. Because a lot of financial data is talking about how something performs over time, how an asset is appreciating or depreciating or whatever. Okay? So that's a line graph. The key there is that we're talking about over time, some variable over time. All right, what about a bar graph? A bar graph consists of bars that are separated from each other. Bar heights represent frequencies, relative frequencies or percents. The chart may be oriented vertically or horizontally. Here's the really important thing. It's used with qualitative data. So a bar graph is used to depict qualitative data. And the bar heights can represent frequencies or percents, relative frequencies, just kind of whatever you would like. So let's see with this example. A prior stats class was surveyed regarding their pets. The survey results are given below. Construct a bar graph that shows the frequency of each pet. Okay, so let's see. So we want to label the axis here. This is our pets. And basically we're going to have a bar for each of our pets. Cat, dog, lizard, snake, etc., etc. There is no inherent order here because there is no order to qualitative data. In qualitative data, you don't order cats, dogs, like lizards don't come before dogs or vice versa. So there is no order. So I'll probably do it in order of how it's listed in the table, but there is no required order. Okay, so let's see. I guess I'll use just C for cat since I don't want to run in a room here. So I'm going to put a bar. So C will be cat, and I'll put a bar above that. And it needs to have a height of 10 because the bars heights are, we're told, represent frequencies. So something like that. And then dog. Okay, there was 19 people had dogs, so I'll just say D for dog. And I need to make this bar almost to the top. Something about like that. But they're separated. Okay, that's important with the bar graph. Lizards, there's 3 people that had lizards. So I'll just say L for lizards. about like that. And then snakes, 4. Well, 4 is just a little bit taller, so maybe like that. S for snake. And fish were 8. Let's see, 8 is maybe about like that. Again, by hand, you're never going to be perfect. It's more about, I want you to understand what this is telling us. Of course, how to make one, but in practically speaking, you'll always be using a computer to make a bar graph. Okay, chickens are C, so I guess we'll do CH for chicken, since we already have C for cat. And that was just 2, so that's a pretty short bar, something like that. So that's a bar graph. Again, if we needed to make a bar graph with relative frequencies, well, then that would take a little more work because we would need to calculate relative frequencies. Of course, if you have relative frequencies, well, then these numbers would not be the way to label this axis because relative frequencies are decimals between 0 and 1. But here, our bar heights represented frequencies. And again, this is qualitative data. These are categories, people that were surveyed, the pets that they had. These are all categories. And again, I oftentimes will have students get confused about the qualitative, quantitative thing because they'll assume that if you just see a number, that means you're working with quantitative data. But remember, these numbers here are frequencies. Basically, think about the scenario where these data came from. I asked my class, I said, hey, what kind of pets do you have? And so I said, cat, and I said, raise your hand if you have a cat. And people raise their hands. Raise your hand if you have a dog. Okay? So it's qualitative data, but just because it's qualitative data, that doesn't mean there's not any numbers anywhere, because, of course, these frequencies represent how many people had cats, dogs, lizards, etc., etc. Okay? One more chart before we start doing some calculations. Let's talk about a histogram. Now, we're not going to make a histogram because you probably, well, the reason you make a histogram is because usually we have a lot of data. Okay? So notice here I made a histogram for 102 test 2 scores. So I don't want to, do a histogram and count the frequencies and stuff. Histograms are best left to a computer because they take a little more work. But basically, a histogram is like a bar graph, except it's made with quantitative data. Okay, with quantitative data, and we allow the boxes to be right beside each other because think about this is grouped data, and think about you have 0 to 9, 10 to 19, 20 to 29, etc. I mean, well, by definition, I mean they're right beside each other. So it makes sense that the bars are adjacent, touching, because this is like a number line down here. Think about a number line from 0 to 100. With a bar graph, there was no number line. These were qualitative data. So there's no number line there. It's just chickens, dogs, cats, lizards, whatever. But here we're working with a number line. So that's why we have the boxes adjoining as they are. But basically, think about the bar heights here are also representing frequencies, just like they were in the bar graph on the previous page. But this is a histogram. Histogram because it's quantitative data we're working with. But you can have histograms where the bar heights are represented by or represent relative frequencies or percents, just like you could with a bar graph. Okay? But again, we're not going to make any of those just because they're best left to let software do that. However, it's important that you understand what's going on here. Again, clearly, I guess I should label this first of all. So this would be the test 2 scores. This would be like score range. score range, and I would say this is F for frequency. Okay? So the frequency of that. So it looks like, 80 to 89, looks like about, 26 or 27 people scored in the 80s. About 22 or 23 scored in A. About 20 people or so scored a C. So yeah, that's what a histogram is telling you. Okay. Now, what about measures of location? Measures of location are observations, are calculations that tell you things like where's the middle of the data, where's the bottom 25% of the data, where's the upper 25% of the data, where's the upper 10% of the data. Okay, there are going to be a lot of words here that you recognize, but we'll need to make sure we're on the same page about what they mean. For instance, percentile, this is probably a word you've heard before, because if you've taken any standardized test, you have gotten your results that probably gave your score in percentile form. Of course, you probably got a raw score too. Like if you took the PSAT or the SAT or the ACT, you're going to get a percentile score as well as your raw score. A percentile is an observation such that some percent of all observations fall below it when you have a ranked data set. That's very important. You have to have a ranked data set. Okay? So basically what a percentile says is, hey, if you're told that your score is the 60th percentile, well, that means that you scored basically better than 60% of the other test takers. Okay? If you scored the 90th percentile, that means your test score is better than 9% of the other test scores. Okay? So that's what a percentile means. You often see the 90th percentile or the 99th percentile. Those are pretty common ones, and actually we'll see a couple more, even more common ones in just a sec. These things are called quartiles. So quartiles are just basically specific percentiles. So percentiles can be, first percentile, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, whatever, 11, 12, 13, 14, up to 99. But quartiles are just three specific ones. The 25th percentile, the 50th percentile, and the 75th percentile. Those are what are called quartiles. They have special names. The first quartile, that's the 25th percentile. It's the observation such that 25% of the data lie below it. Of course, when the data are ranked from least to greatest. We have a shorthand notation for the first quartile. It's Q1. Q1 is the first quartile. Second quartile, this is also called the 50th percentile or the median. It is the observation such that half of the data lie below it, which means half the data lie above it. Okay? So if you made a 50th, if your score was the 50th percentile, it doesn't necessarily mean that your score was bad. It just means you scored better than half the class, worse than half the class. But just for the sake of argument, let's say that everybody made an A. If everybody in the class made an A on the test, well, the 50th percentile would still be an A, still a good score. So these are measures of location, compared. It's how does this observation compare to the rest of the observations? It's not, is this an absolute good observation, low or high? Is it, how does this observation compare to the rest? That's what these are called measures of location. Okay? The third quartile is called Q3. It's the observation such that 75% of the data lie below it in a ranked data set. It's also called the 75th percentile. So again, keep this straight. I know it's kind of confusing, but The first quartile, we abbreviate as Q1. It's also called the 25th percentile. I mean, that's what it is. We're going to have a percentile formula to calculate percentiles. And so to calculate the first quartile, we're actually just going to calculate the 25th percentile. To calculate the second quartile, the median, we're actually going to calculate the 50th percentile. And to calculate Q3, the third quartile, we're going to calculate the 75th percentile because we have a percentile formula below. Okay? Very important to understand, these are test scores. Or, these are scores. These are observations. So, like, if you scored a 75 on the test, we would say and let's say the 75 was better than 30% of the rest of the scores. So we would say that the score of a 75 is the 30th percentile. Okay? It is the score such that 30% of scores are less than it. Okay? So the third quartile is some observation such that 75% of the observations are below it. 25 or above, 75 or below. Okay? Interquartile range, it's a really easy formula. It's just the spread of the middle half of the data. It's Q3 minus Q1. So to calculate an interquartile range, you just have to find Q1 first, or find Q3, and find Q1, and subtract. That's it. Super easy calculation, but you do have to find Q1 and Q3 first. All right. Let's look at a formula to find a percentile, which will allow us to find quartiles also. Now, it might look like a bunch of directions here that are complicated, but it's not too bad once you figure out what's going on. So so there's a K in our formula. K is the percentile you want to calculate. 70, 75, 20, 25, 50, 30, 10, 5, 1. It's whatever percentile you want to calculate. I is the index. It's the position of a value in a ranked data set. So we're going to calculate what's called the index. Our answer is going to be like 5. Well, that means to look for the 5th value in a ranked data set. Or if our answer for the index I is 8, then that means we're looking for the 8th value in a ranked data set. Lowercase n is the total number of data. Oh, I should say datums there. That's a little typo. Total number of datums. Or I should say observations. Maybe that's better. Total number of observations. Okay? So the first step when you're finding a percentile is always to rank the data first. If you try to do any other steps without ranking the data, you're almost always going to get the wrong answer. You could get lucky maybe and get the right answer still, but it's very unlikely. So rank the data and then compute this value for I. So you plug in your K, plug in your N, type it into your calculator, and get I. Now there's a couple possibilities here. You could get a whole number. That's the good, nice thing. If you get a whole number, then basically the kth percentile is the data value in the ith position of a ordered set. In the ordered set. Oh, there's a typo. Set of data. Scratch that. Okay. So like you're going to calculate I. Let's say it's a 5. That means you're looking, not that 5 is not your answer. 5 is you're looking for the 5th value in your ranked data set. Okay? What happens if I is like a decimal number? Well, then you have to round I up and down to the nearest whole numbers and take the mean of the average of those two positions. Take the mean average of the values in those two positions. So I know this might be a little kind of confusing. So what I'm going to do is we're going to skip to the next page real fast, do an example, and show how this works. Okay? Because there is one more definition here, one more formula, but I want to show you how to do percentiles first. Okay, so top of the next page. The data set below is composed of the salaries of all 11 employees of a small company. Okay? Calculate Q1, Q2, and Q3, so that's the first, second, and third quartile. Interquartile range, 75th percentile, 35th percentile, and identifying outliers. And we haven't talked about percentile rank, so we'll have to come back to that. So let's do the quartiles and percentiles first. Okay, now what you have to do before you even talk about any calculations is you have to rank the data. Okay, so sometimes the data will be ranked for you. Whenever I was creating all your homework assignments, basically for most of the questions that have you calculate percentiles or quartiles, basically I have the homework system randomize whether you are given ranked or unordered data. So sometimes, basically, on average, half the problems you'll get that pertain to percentiles and quartiles, half those problems you'll get ranked data, and half of them you'll get unranked data. So it looks to me like these are not in the correct order. These are not ranked from least to greatest. So I need to rank them from least to greatest before I can even get started. So let's see here. Least to greatest looks like 2,000 is the smallest. So I'm just going to cross that out. I'm going to go over here. I'm going to go over here, and I'm just going to order my numbers up here, I think. Hopefully there's room. 2,000, if I write small enough. Okay, 2,000, that's the smallest one. Now what's the next smallest one? 40, so far, 40, 28. So 28,000. So 28,000. Mark that one off. I think 33,000 is next. So 33,000. Cross that one off. 33 looks like 40,500. Okay. 40,000, 42,000, I guess. 42,000. What's next? 54 maybe? Yeah, 54,000. Oh, we have two 54,000s. So 54,000 twice, and you can't neglect writing the duplicates. You have to keep both of them. So 54,000, then looks like 64,500. Then 68,500. Okay, 69,000 and 120,000. Okay. Now let's make sure I have, should be 11 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I think, yeah, we should be good there. So we ranked the data. Okay. Now, let me just glance back at our formula on the previous page. What we want to do, okay, we want to calculate Q1 first. That's the first quartile. The first quartile is also known as the 25th percentile. So let me just write real quick over here. So here's the notation for percentiles. It's like a capital P with a subscript, whatever the percentile is. So that's the 25th percentile. So the 25th percentile is the first quartile. The 50th percentile is the same thing as the second quartile. And the 75th percentile is the same thing as the third quartile. Okay? So we're going to calculate quartiles, we actually just calculate the correct percentile. Okay? So let's do the 25th percentile first, which is the first quartile. And so we're going to do the 25th percentile and look at this formula. So the formula says we plug in k is 25, and then n is the total number of observations. So we had 11 observations in our data set. Okay, so we go over here. And to calculate the first quartile, we're going to calculate I. Now, I is the index, and what you do is k over 100 times n plus 1, where n is the number of observations, so 11 plus 1. Now, that's actually not a hard calculation, right? Because 11 plus 1 is 12. 25 over 100, that's like 1 over 4. So 1 over 4 times 12 is 3. If you don't feel comfortable doing that in your head, no worries. Just type it in. Just make sure to use parentheses, of course. So 25, or do separate calculations, like 25 over 100. Oh, don't type the wrong thing in. 25 over 100, it's 0.25, 1/4, times 11 plus 1, times 11 plus 1 is 12, so you have to get 3. Now here is where a very common mistake comes into play. If you're not thinking about this, a lot of people just say 3 is the answer. Done. 3. But 3 is I, the index. What that means is you're looking for the third position. You're looking for the third position in your ranked data set. So 1, 2, 3, there is Q1. Okay? Let's do Q2. So the 50th percentile. So Q2, again, we calculate I, the index. Now Q2 is the 50th percentile. So it's the exact same calculation over here, except instead of 25 over 100, it's going to be 50 over 100. So 50 over 100 times number of observations plus 1. Well, again, that's 12, and that's 1/2. So 12 times 1/2 is 6. So now we're looking for the 6th position. That's going to be Q2. So first position, second, third, fourth, fifth, sixth. So there is the second quartile, Q2, also known as the 50th percentile. Okay? And now let's do the third quartile. The third quartile, recall, is the 75th percentile. So let's see. Calculate Q3. We need I equals now 75 over 100 times 11 plus 1. Okay, well that's 75 over 100, that's 3/4. 3/4 times 12. Well, let's see, that 3/4 times 12 is 8, I believe. Okay. Again, if you don't want to do that in your head, no worries. Just do 75 over 100 times 12. Oh, a good thing I did, because I said 8, and my mental arithmetic was wrong. 9. That happens a fair amount. Yeah, because, okay, yeah. 3/4 times 12, it would be 3 times 12, which is 36 divided by 4 is 9. Yeah. Okay. So, again, 9 is not the answer. Of course, 9 wouldn't make any sense at all because all these numbers are in the thousands. It doesn't make any sense that the third quartile be $9. Okay, it's the 9th position. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There is Q3, the third quartile, which again is the same thing as the 75th percentile. So interquartile range is now easy. Interquartile range is just Q3 minus Q1. So let's see, what's Q3 minus Q1? That is 68,500 minus Q1, 33,000. So it looks like 35,500. 35,500. Okay. Now, 70th and 35th percentile. All right, so let's see. P70, that's the 70th percentile, kind of like that. It's the exact same formula because you're calculating the index. I is what? 70 over 100 times the number of observations plus 1. Okay? Now, I don't know this one off the top of my head. Basically, what's 70% of 12? Not sure. So 70 over 100, 0.7, times 11 plus 1, so times 12, 8.4. Okay, so this is good because this was talked about in the instructions on the previous page. What happens if you don't get a whole number? We got a whole number for I for these 3 times. Oh, I didn't write it there. 9th position. We got a whole number. Now, what happens if you don't get a whole number? Well, what you have to do is you have to look at the 8th position and the 9th position and take the average of those two. So again, round down to 8, round up to 9, and take the average of those two values in your data set. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. There's the 8th position. There's the 9th position. So the 70th percentile would be the average of those two values. Okay, so P70 is the average of those two values. So the average of the 8th position, 64,500, and the 9th position, 68,500, divided by 2, and so 66,500. There was a note on the previous page that said sometimes a percentile or a quartile is actually a number that's not in your data set. 66,500 is not in our data set anywhere. And that happens sometimes. When it happens is actually when your index is not a whole number. Here our index, I didn't write down, was 8.4. So we had to round 8.4 up and down to 8 and 9 and take the average of the 8th and 9th positions to get 66,500. Now, let's see if we get any lucky with the 35th percentile. So P35, okay, we're going to calculate the index would be 35 over 100 times 11 plus 1. Now, let's see here. I doubt we're going to get a whole number here. So 35 over 100, 0.35 times 12. 4.2. So we get 4.2. Again, that's not a whole number. So we have to round that down to 4, round it up to 5, and take the average of the 4th and 5th positions. So let's see what we end up getting here. P35 equals, okay, the 4th and the 5th positions. Let's see. 1st, 2nd, 3rd, there's the 4th position and the 5th position, these two. So 40,500 plus 42,000 divide by 2 to find their average, 41,250. Okay. So those take a little more work whenever you don't get a whole number for your index. If you get a whole number for your index, that's not too bad at all. Just a matter of finding those positions. Okay? Let's see. The thing we skipped on the previous page was called percentile rank. Okay? Percentile rank is basically just the percent of data that are below a given observation. But there is a formula that kind of takes into account if there's any repeats. So let's take a look real fast. The bottom of the previous page, percentile rank. So the definition here is pretty straightforward. It's just the percent of data that fall below a specific observation. And of course, just like with percentiles and quartiles, the data have to be ranked. So to calculate a percentile rank of some observation A, first rank the data, then let X be the number of values less than A in the ranked data set, and let Y be the frequency of A. Remember what frequency means? Frequency is just the number of times an observation is present. So if it's not repeated at all, it'll have a percentile. It'll have a frequency of 1. If there's 2 of them, it'll have a frequency of 2, 3, whatever, etc. So you have to first of all calculate the numbers of observations less than the given observation, and then calculate the number of times the observation was repeated, and then just plug into the formula. X plus 0.5y divided by n, where n's the total number of observations, like always, then multiply by 100, and there's your answer. So let's see. Percentile rank, here I'm out of room here, so I'll use this scrap paper. If you want to do the percentile rank of, the first one is 54,000. Okay, what we need to do is calculate the number of, or not calculate, really just count the number of values that are less than 54,000. So let's see. 1, 2, 3, 4, 5. So we're going to plug into our formula. That's 5 plus, so here I'll write our formula with the blanks missing. Okay, so it's the number of observations less than the number 54,000 plus 0.5 times the frequency of 54,000. How many times is 54,000 present in our data set? Well, it's present twice. Oh, sorry, you can't see that. It's present twice. There's 2 54,000. So the frequency is 2. Then we divide by the total number of observations, 11 employees, and that's our calculation. Use a calculator. Let's see. So let's see. It's going to be 5 plus 0.5 times 2, which is just 1. 5 plus 1 gives you 6. Divide by 11 times 100. So the percentile rank, if we round this, it's going to be about 54, 0.5 if we round to 1 decimal place. So the percentile rank of 54,000 is 54.5%. So basically that means approximately 54.5% of the data lie below 54,000. It is approximately. It's not exact because, well, when you work with small data sets, it's never going to be exact. But approximately 54% of the data are below the observation 54,000 when you have a ranked data set. Now, what about the percentile rank of 40,500? So same basic calculation. Okay. The denominator is still 11 right there because there's 11 observations. So we first need to calculate how many observations are below 40,500 in your ranked data set. So there are 1, 2, 3 observations below 40,500. So 1, 2, 3 plus, you use 0.5 times the frequency of the given value. So what's the frequency of 40,500? How many times is it present in the data set? Well, it's only present once. So the frequency of 40,500 is 1. And then we just type that into our calculator, carefully of course, to get the approximate percentile rank. So let's see, 3 plus 1/2 times 1, well, that's just 1/2. So 3 plus 1/2 is 3.5 divided by 11 times 100. And so we get the approximate percentile rank is 31.8%. This means that approximately 31.8% of the data are below 40,500 in the ranked data set. Okay? So when I first encountered all these terms years ago, I remember it took me a while to keep them all straight. Percentiles, percentile rank, it all just kind of goes together. But just remember, percentile rank is just, we have a formula, of course, but basically it's just the percent of data below a given value. That's the percentile rank. How much data, what percent of data are below that given value. Percentiles, of which quartiles are a specific type, percentiles are just usually an observation such that some percent of data are below it. Excuse me. And they're not always in the data set. Like here, was the 75th percentile, also called the third quartile. It was an observation in our data set. The interpretation there is that approximately 75% of the data are below Q3. Q2 is the 50th percentile, also called the median. Approximately 50% of the data are above it, 50% are below it. Q1, also called the 25th percentile, the interpretation is approximately 25% of the data are below it, 75% are above it. Okay, also called the 25th percentile. Now these are all approximate, again, like I said, because that's how, it's not exactly, the numbers don't exactly always work out to exactly 25%, exactly 50% of the data when you're working with pretty small data sets. Okay, so these are all, again, measures of location, okay? How the data compare to each other, basically. Now, outliers, basically, well, I'll talk about outliers for a little more when we do box plots in just a sec. But remember, outliers are the values that are much unlike the rest. So I'm looking at this ranked data set, and I see 120,000 over here, that seems to me way bigger than most. Like you have numbers in the 50,000, 40,000, 60s, and you have 120K. That's almost double even the rest of the high numbers in the data set, or it's even more than double most of them. So I would say, in my estimation, 120,000 would probably be an outlier. Excuse me, sorry about that. And also, looking over here, 2,000 is way lower than the rest. I would say 2,000 is also an outlier. Okay, again, we'll talk maybe a little more specifically about outliers soon, but remember, outlier is just an observation that's unlike the rest. It's really high or it's really low. It's unlike the rest. Not necessarily a cause for concern, but could be. All right, now what's a box and whisker plot? Basically, a box and whisker plot, also called a box plot, is a way to display data. Of course, it's a graph, and it includes the quartiles, Q1, Q2, and Q3, and it's nice because it tells you where most of the data are concentrated. Okay, so it allows you to get some good information just by glancing the graph. It also shows a good representation of the spread and the skewness of the data. So there's three nice visual characteristics. It shows the center, spread, and skewness. We haven't talked about this word skewness, but I'll get more into that in just a sec. And the way you calculate or the way you construct a box and whisker plot, I'll show you in just a sec. But just notice it is composed of 5 values: the minimum value, the maximum value, and the quartiles, Q1, Q2, and Q3. So what do? Here are the instructions. So just like always, you got to rank the data first. Just, the past page and a half, the first instructions have been rank the data first. So that means least to greatest. Then you need to calculate the maximum value, the minimum value. That's easy. You're not really calculating those. That's just the highest and the lowest. But you do need to calculate Q1, Q2, and Q3. And then once we have those in our hand, then we'll talk about these instructions about exactly how to make a box and whisker plot. Okay, so let's see. We probably need a little more room here. So, well, actually, I guess we have some room here. So I'll put the data down there. I'll rank them down there. Okay, so we want to rank these data. They are currently not ranked from least to greatest, clearly. So we do need to rank them first. So let's see here. Looks like 69 is the smallest. '74, 75. Okay, maybe 79. 81, 84. 90, 94. 98. 104, 112. 144. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, I think we're good. Okay? So we need to find Q1, Q2, and Q3. Of course, we need the maximum and minimum values, but there they are. Those are easy. Okay? So let's see. For Q1, we need to calculate I. So here, I don't want to say equals anything because remember, I is not our answer. I is just the index of our answer for Q1. So for Q1, the index is going to be, okay, so it's the 25th percentile. So 25 over 100 times 12 plus 1. That's going to be our index. So basically it's 25 over 100, that's 1 over 4, times 13. So that's basically 13 over 4. 13 over 4, 3.25. Okay. So remember what happens. Oh, sorry, it's so crammed there. 3.25. Okay, so remember what happens if you have a decimal. Basically, that means you have to round that number down and up to the nearest whole number, so that would be 3 and 4. Now, that means we're looking at the third and fourth position, and we're going to average those two numbers. So 1, 2, 3, 4. So basically, we're going to average these two numbers, and that's going to be Q1. So let's see. Q1 ends up being, well, 75 plus 79. By the way, don't make this mistake. I see that all the time. Okay, the calculator knows the order of operations, which means it's going to do the division first and then the addition the way I have it typed here. What we want to do is if you want to use just in one quick calculation, you need to do 75 plus 79 close parentheses divided by 2 to get 77. Or you can do 75 plus 79 enter divided by 2 to get 77. So there's Q1 is 77. Now Q2, we have to calculate I, and it's 50, because this is the 50th percentile, is Q2, times 12 plus 1. Okay, so basically that's 1/2 is, 50 over 100 is 1/2 times 13, or 13 over 2. Now, of course, 13 over 2 is 6.5. That means we're looking at the 6th and 7th positions. Round 6.5 up, round it down. So you get the 6th and 7th positions. Okay, so 1st, 2nd, 3rd, 4th, 5th, 6th, and 7th. There, and the average of those two will be Q2. Okay, so Q2, let's see, 84 plus 90 divided by 2, 87. And then for Q3 is the 75th percentile, so we're going to calculate the index to be 75 over 100 times 12 plus 1. So again, 13 is 12 plus 1. 75 over 100, that's 3/4. So 0.75 times 13, 9.75. So we have to round down and up. So that's going to be the 9th and 10th positions. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 9th and 10th positions. So we take the arithmetic average of those two values. So 98 plus 104 divided by 2, you get 101. Okay, so it takes a little more work whenever you don't get whole numbers for your indices, but it's not too much extra work. So now we have Q1, Q2, and Q3. Of course, our minimum value is just the smallest, which in our list is 69. And our maximum value is the largest in our list, 144. And now to make what's called a box and whisker plot, take your number line down here. What we want to do is put a vertical line above Q1, Q2, and Q3. So Q1 is 77, so I don't know, maybe about like right there. Put a vertical line like that. Then a similar vertical line at 87. So 87, you know, like that. Try to make them match, you know, the same height. But they want to be a little bit above the number line. Then do the same thing at Q3, 101. So about like that. And then connect them to make a box. So here I'll kind of do this. Like so. So there's your box of your box and whisker plot. Then what you want to do is make the whiskers. So the whiskers extend out to your maximum and minimum value. So the minimum value is 69, so put a little vertical line there, kind of like that. And then draw a horizontal line to your box like so. And then do the same thing on the right-hand side, 144, you know, a little vertical line, and then draw a horizontal line out to there, and there are your two whiskers. So your box and your whiskers. Now, you know, basically what we're seeing here is if, you know, that's Q1 right there, that's Q2 is that vertical line, and Q3 is that vertical line. So basically, the interquartile range, the middle 50% of the data, are represented by that box. So that's where the middle 50% of the data are. That's where the bulk of the data are. That's where we said shows the center. There's the center. Okay? The center is where the box is. Spread, well, the spread is denoted by the left and right whisker. The data spread to about 70 and to about 145, you know, specifically 144 and 69. But you know, from this, just glancing at the graph, you say, okay, those data values range from about 70 to about 145. So that's the spread. Now skewness, skewness we haven't talked about yet. Here, let me just glance at the next page to show you skewness. Skewness, excuse me, is talking about the shape of the graph. So basically, you can have a symmetric graph, which just means basically the two halves of the graph are mirror images of each other. So think about if you draw a vertical line here, or like you can imagine folding the paper, well, the graphs would match, the two halves would be mirror images of each other. It's symmetric. Likewise here, this is called a uniform graph specifically, but again, you could draw like a vertical line right where my pencil is, fold the paper, and the two halves of the graph would be mirror images of each other. However, that would not be the case right here. These are not, there are not two halves that are mirror images of each other here. These are both called skewed graphs. Now, right skewed is the situation where you have a data that are trailing off to the right. We call that the tail of the data, where the data are kind of getting smaller, smaller, smaller. The bars are getting smaller and smaller. That's the right skewed distribution. Now, think about what those bars mean. Remember, tall bars are where there's lots of data. Short bars are where there's very little data. So a right skewed distribution means there's less data on the right side of the distribution because that's where the short bars are. It means the more data are on the left side. So a right skewed distribution means there's less data on the right side. Likewise, or I guess maybe similarly, a left skewed distribution means that less data are on the left side of the distribution. So that's where the short bars are. Short bars represent little data. Tall bars represent more data. So that we would say like the bulk of the data are on the right side here, less data are on the left side. The data are trailing off to the left. Okay? So left skew means we say the tail is on the left side, or the data are trailing off to the left. Right skewed, the data are trailing off to the right. There's less data on the right side. Now, how do we translate that into a box and whisker plot? Think about it this way. I mean, we see no bars anywhere in bar heights, but think about what this graph is telling us. Okay, there's the median, Q2, the 50th percentile. That means half of the data are on that side to the left, half of the data are on that side to the right. Which side is more spread out? And remember, when data are more spread out, it's going to lead to shorter bars. So basically half the data are spread out over that distance. Half the data are spread out over that distance. Which side is more concentrated? Well, this side is more concentrated. What does that mean? That means you're going to have the same amount of data over the span of a few bars, or the same amount of data over the span of a lot of different bars if you were going to make like a chart here, like a histogram. So that means this half of the data are more spread out. This half of the data are more concentrated, which is going to result in there being higher, the distribution being higher over here and shorter over here. So you can see this is going to be a right-skewed graph, because what would happen was, like the bar heights on the left-hand side would be pretty high and would trail off to the right like that, because half of the data are right there, half of the data are right there, but the right-hand side are more spread out, so the data would be trailing off if you had like a bar graph. Okay, that's how you can get skewness. So again, center is basically where the box is. Spread, well, that's the whiskers. The left whisker to the right whisker is the spread, and the skewness, basically, it's going to be skewed where on the wider half of the graph. So here, which side is more, which half is wider? The right half, so I'm looking from the Q2 to the right, that's wider on the right-hand side than Q2 to the left. So it's going to have skewness on the right hand. Okay? So that's a box plot, and again, they're pretty useful. I see them a lot in certain types of literature. So, it's useful to understand what a box plot is telling you. Now, we did measures of location. Now, what about measures of center? Okay, measures of center, you will be familiar with a couple of these. Yeah, the median. Well, the median is the observation that marks the middle of a ranked data set. It's the same thing as the second quartile or the 50th percentile. So we just got through calculating a bunch of medians. Q2, that's also called the median. It's also called the 50th percentile. So nothing new there to calculate. It's just the exact same calculation from before. Mode, you probably are familiar with the mode. It's the observation with the highest frequency. It's possible to have no mode, a single mode, or you can have multiple modes. Like sometimes I give a test and nobody makes the same score. In that case, there is no mode. Other times I give a test and, say like 5 people make an 80, and that's the score with the highest frequency, then that would be the mode. but let's say 5 people make an 80 and 5 people make a 75. Well, if 5 is the highest number of repetitions for a single score, then both 75 and 80 would be a mode. Okay? But here's a common mistake. Just because a observation is repeated doesn't automatically make it a mode. For instance, let's say I give a test and 2 people make a 90, but 3 people make an 85. Well, then 85 is the mode because 3 was the highest frequency. Even though 2 people scored a 90, it's not automatically a mode because it wasn't the score with the highest frequency. So it has to be the score with the highest frequency. And then the mean here, the mean, again, we've talked about this. It's commonly what you call the average. Okay, it's when you add up all the values and divide by the number of values you have. That's the mean. Okay, so let's see what we have here. Formula time. Okay, we're gonna have lots of formulas over the next page or two. So make sure to you don't have to memorize them. Of course, we have a formula sheet. Okay, formula sheet for you that you can print off on the guide notes again. But there's going to be a lot of formulas here. So for chapter 2, we've already talked about all these, and now we are down to these, and we're going to have all these still to go, and those before chapter 2 is over. So chapter 2 has a lot of formulas. All right, but a lot of them go together. That's the thing. Like, they're not necessarily there are technically different formulas, but they kind of go together with little tweaks. So a sample mean. Okay, so first of all, we got to understand we're going to have different formulas for grouped data, grouped versus ungrouped. Okay. So grouped data, that's like when you have, I don't have the notes with me, but like the notes from chapter 1, where you have different classes, like the class from 0 to 9, and 10 to 19, and 20 to 29. That's grouped data. Ungrouped data is just when you have a list of numbers. Like those are ungrouped data, just a list of numbers. Here's an example. Yeah, we're about to have one. Grouped data like this. Whenever you have a class with ranges like so, that's grouped data. You have a chart like this. Ungrouped data, just have a list of numbers. Okay, so what's the formula for a sample mean for ungrouped data? First of all, what's the symbol? The symbol is X bar. X bar, forever and ever, is going to represent the sample mean. So just go ahead and commit that to memory. It's X with a little bar above. We call it X bar. X bar is what? It's the sum of the X's over sample size. So sigma, we talked about that in chapter 1. It's sigma X, the sum of the X's over sample size. Okay, what about population mean? Population mean is always going to be represented by the Greek letter mu. Again, it's Greek letter mu. 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 Okay. It is going to be the sum of the x's over capital N. Now we got to make sure to be intentional here with the capital letters versus lowercase letters. A lowercase n always means sample size. An uppercase n always means population size. So you have to be intentional. If you always write your letters capital or lowercase, well, you need to rethink that because capital N versus lowercase n do make a difference here. Okay. Now, practically speaking, those formulas are both telling you the same thing. They're both telling you to add up all the values and then divide by the number you have. Okay? So in general, you want to be very careful with determining whether you have population data or sample data, because usually the formula for a sample calculation is going to be different than the calculation for a population. However, here, that's not an issue because practically you're doing the same thing. You're adding up the observations, divide by the number of observations. Add the observations, divide. Now, what about for grouped data? To calculate the mean of a grouped data set, again, for a sample, the symbol is still x bar, but the formula is going to be the sum of the m times f's over n, where m is the class midpoint. So, again, that's why we did practice in Chapter 1 about summing when you have the product of two numbers. So here this says multiply all your m times f's, then add them all, then divide by lowercase n. For population, again, it's mu is the symbol. And it's the sum of the m times f's, same numerator, divided by population size. But again, practically you're doing the same thing. You won't get into trouble here if you, say, accidentally use the wrong formula, but that you won't be so lucky with other calculations. Okay? All right, let's do a couple more formulas, and then we will do a few calculations using these. Actually, I lied. We're going to do a couple examples, then we'll come back. We'll do a couple examples, then we'll come back to grouped data. So here's a data set. The number of books checked out from the library from 25 IRSC students are as follows. Okay. So we have 25 observations, and we want to calculate the median, mean, and mode. Okay, let's do the easy one first. What's the mode? Well, which one's repeated the most? Looking here, okay, 0 is repeated 3 times. 1 is repeated once, so 2 is repeated once. So far, 0 has the highest frequency. Oh, 7s, though, have 7s. 1, 2, 3, 4 7s. So 7 so far has the highest frequency. There are 3 8s, but there's 4 7s, so 8's not going to be the mode. 1 9, 1 10. Okay, it looks like 7 is going to be the mode. Okay, because there's 4 7s. Again, like I said earlier, just because an observation gets repeated doesn't automatically mean it's going to be a mode. Here, 0 was repeated 3 times, and 8 was repeated 3 times, but 7 was repeated 4 times, so 7 is the mode. Now, median, okay, median, that's the 50th percentile. So to calculate the median, same thing as the 50th percentile, which is the same thing as the second quartile. Well, we need to calculate the index. The index is 50 over 100 times the number of observations plus 1. So there's 25 observations plus 1. So let's see, we can do that in our head actually, right? Because 25 plus 1 is 26. This is 26 times 1/2, so I is 13. But, okay, don't go on autopilot. 13 is not our answer. That's the index of our answer. So we want to rank our data. Now, it looks like I ranked our data, but, it's in rows. So 13th position. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it turns out that 7 is our median and our mode. Okay? Now the mean, well, that's when you add them all up and divide by the samples. Well, here, okay, I guess we need to ask ourselves, is this a sample or is it a population? Let's see. The number of books, usually there will be indicator words, keywords in the instructions. The number of books checked out from the library from 25 IRSC students. So if this was population data, it would be all IRSC students. Do you suppose 25 students are all IRSC students? Don't think so. There's a whole lot more than 25 students. So this is sample data because it's only talking about 25, out of like 20,000. Okay? So this is sample data. It's not so important whenever you're just calculating a mean, but it will be very important for many problems we work throughout the rest of the class. So it's always good to ask yourself the question, are we working with sample data or population data? So that means we're going to calculate an X bar for a sample mean. This is ungrouped data, just a list of numbers. So we need to do the sum of the X's divided by sample size. Now the sample size was 25. That's easy. We're told it's 25 students. So that's the denominator. But the numerator is going to be the sum of the X's. Just add up all the data values. So let's see. 0 plus 0 plus 1 plus 2 plus 3 plus 3 plus 4 plus 4 plus 5 plus 5 plus 7 plus 7 plus 7 plus 7 plus 8 plus 8 plus 8 plus 9 plus 10 plus 10 plus 11 plus 11 plus 12 plus 12. I'm going to assume that I typed those in correctly, and 154 is the sum of the X's. So let's see, 154 over 25, 6.16. So that's the average number of books checked out by this sample. So X bar is 6.16. Okay? Now, what else do we have here? So we calculated the mean, median, and mode. Now let's talk about how these are related to each other in terms of skewness and pictures here. Okay? So we skipped here just a few minutes ago and talked about skewness, but how is skewness related to, or how are the mean and median related to how a distribution skewed or not? So remember what we talked about a few minutes ago. A symmetric distribution is basically when you can divide the graph in half and have two mirror images of each other. So divide it in half vertically somewhere. Like you can draw a vertical line like right here in the middle, and you have two mirror images. A uniform distribution is also symmetric. A symmetric distribution can be lots of different ways. I mean, it's kind of hard to draw freehand. But let's say you could also have like a symmetric distribution, something like that would be, I didn't draw it perfectly, obviously, but if you kind of drew a vertical line right there, and I drew it perfectly, it would be a symmetric distribution. So you can have all types of different shaped distributions that are symmetric. This is one specific symmetric distribution. So basically, if a distribution is not symmetric, it's going to be skewed left or right. So you're going to have a tail on the left side or right side. Now, remember what I said earlier, and looking at these graphs, where the graph is tall, that means there's more data. Where the graph is short, there's less data, because bar heights represent data. the amount of data. So here, a skewed right distribution has less data on the right side. A skewed left distribution has less data on the left side. Now, how does that relate to the mean and the median? Well, if you have a left-tailed distribution, the mean is usually less, and I say usually, that's a very important word, usually less than the median and mode. So if you have a left distribution, left skewed distribution, the mean is going to be skewed over here somewhere to the left. By the way, the mode is always easy to pick out from a graph because the mode is represented by the tallest bar. So the mode here would be this observation with the tallest bar. Okay. So if you have a left-tailed, left-skewed distribution, the mean is usually smaller than the median and mode. So like the mean would be over here somewhere, and the median and mode would be over here. Now the opposite is usually true for a right-skewed distribution. Again, I need to underline the word usually, but on a right-skewed distribution like this, usually the mean is greater than. So the mean would be over here somewhere, and the median and mode would be over here somewhere. Of course, the tallest bar, that would be the mode. But the median would be over here. Basically, what's happening there is the mean is really susceptible to extreme values, to outliers. So if you have, like, think about your number line. When I say bigger numbers, I mean to the right here. Your bigger numbers are on the right, your smaller numbers on the left. So the mean gets pulled up or down easily, whereas the median not so much. Okay, that's why if you have a right-skewed distribution, the mean is usually pulled to the right. If you have a left-skewed distribution, the mean is usually pulled to the left because the mean is easily influenced by outliers or extreme values. Okay. Think about what a uniform distribution means. A uniform distribution, if bar heights represent frequencies or relative frequencies, what does that mean? That means that every class has the same frequency. Or if it's a relative frequency graph, relative frequency. Okay? Because that's what it means to all the bars have exactly the same height. That this class contains the same number of observations as this class, as this class, as this class. They're all the same. They all have the same number of observations. So this would be like if you took a test and like I categorized it as like say like A's, B's, C's, and D's, or maybe like, so I guess like 90 to 100, 80 to 89, etc., etc. And like the same number of people fell in each class. Like there was 5 A's, there was 5 B's, there was 5 C's, 5 D's, 5 F's, or whatever. Okay, that would be a uniform distribution because there's the same number of observations in each class. That's what a uniform distribution is. Okay. By the way, for tests, you guys prefer left-skewed distributions. Because what does that mean? It means there was more scores up in the A and B range. There was less scores over here to the left, low scores. High scores on the right, low scores on the left. Think about a number line like 0 to 100. Here, I mean, obviously here it's 1 to 6, but think about a test would be 0 to 100. You want there to be high bars above like 90s and 80s and stuff like that. Excuse me. You want low bars, less frequencies above like F's and D's and stuff. This would be a very bad distribution for a test. Again, imagine instead of 1 through 8, it's 0 through 100. This would mean there was a whole bunch of very low scores and very little high scores. That's exactly what we don't want for a test. Okay, we don't want a whole bunch of people to fail the test and very few people pass the test. This is the kind of distribution you want for a test. I mean, ideally, I suppose this is what you want. You want There would be average score, and then, some scores that are below average, some that are above average, a few that are really high above average, and a few that are really below average. I mean, that's, like when you say grading on a curve, this is really what you mean here, is literally it's a bell-shaped curve, but, that's sometimes a controversial topic. Okay? All right, what about measures of spread? Measures of spread, there are several. The first is called the range. Now, you may be familiar with the range. Range is simply the absolute spread of the data. It's the maximum value minus the smallest value. The greatest observation minus the least observation. Okay? Usually it's not very helpful, to be honest with you. Like, if I give a test, I never even really bother calculating the range because, sometimes somebody will ace a test, and usually somebody skips a test. So if your greatest value is 100 and your lowest value is 0, well, the range is 100. 100 minus 0 is 100, which doesn't really help you with much. What does that tell you? Not much. Okay? So range isn't very helpful most of the time. But, of course, it's certainly something that we can talk about, calculate occasionally, but not super helpful. Now, what is helpful is something called the standard deviation. But to get to the standard deviation, we have to calculate something called the variance first. The variance is the average of the squared differences from the mean. And I put here in parentheses, it's not particularly useful for helpful for us in this class. Basically, we use it as a stepping stone. Now, that's not true in general if you went to more advanced classes, but for us in this class, the only reason we calculate variance is to then immediately get standard deviation. The reason we don't really do much with variance is because the units are not very good for us. Very, very important. The units on variance are squared. This means, like, let's say the data set you're working with is dollars. If you calculate variance, well, variance is going to be measured in dollars squared, which doesn't make really any sense. If your data set was in seconds, then the variance would be seconds squared, which again doesn't make any sense. However, standard deviation is in the correct units. The standard deviation is a calculated value that measures how far data values are from the mean on average, and the reason we prefer it over the variance is that it is measured in the same units as the original data. So if your original data is in dollars, standard deviation will be in dollars. If your original data are in pounds, the standard deviation will be in pounds also. This is why we prefer standard deviation as our gold standard measure of variance. What it does is it tells you how far away from the mean on average all of your observations are. So if you have a high standard deviation, that means your data are very spread out all over the place. Like if I give you a test and people make A's, B's, C's, D's, F's, 20s, 30s, 40s, if the scores are just all over the place, that's going to lead to a high standard deviation. Or if I give you a test and say like everybody makes an 80, not like exactly an 80, but like a B. Everybody makes a B, that means all the scores are between 80 and 89. That means all those scores are really close together, which will lead to a low standard deviation. So if the data are spread out, then you have a very high standard deviation. If all the data are close together, you're going to have a low standard deviation. Now, we're going to have one set of formulas for group data, another set of formulas for ungrouped data. Now, remember, the grouped data is like this, where you have a chart with classes, grouped data. You're grouping 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 50, et cetera, et cetera. Okay? You're grouping your data. That's grouped data. Ungrouped data is what we usually work with. We almost always in this class are going to be working with group data. Now, in this chapter, you'll have a handful of exercises, and you'll have test questions too where you have to work with group data. But almost always, after this chapter especially, we're going to be working with ungrouped data. So here, I'll just go ahead and divide this, just to make sure we understand there's two different sets of formulas: grouped data, ungrouped data. So how do you calculate variance for grouped data? Okay, so variance for grouped data, the symbol, and the sample variance. The symbol is S. And I should say that I need to specify it's lowercase. It's kind of hard to tell without comparing it, but it's a lowercase s for sample variance equals, okay, let's see, it's a big fraction. On the top of that fraction is, for group data, it's the sum of the m squared f's minus the sum of the m f's squared divided by n divided by n minus 1. Sample variance. Okay, is that a terrible calculation? No, it's kind of tedious, but it's not terrible. Here's the nice thing. Standard deviation. Oh, sorry, I said that wrong. The symbol is s squared. I'm not sure what I was thinking. Sample variance is s squared. Standard deviation is s. That's what I was thinking about. Here's the thing. If you calculate the variance, which is s squared, standard deviation is s. So think about how do you go from s squared to s? What do you do if you want s, but you have s squared? What do? You take the square root. Now, what you will see, if you look at our formula sheet, you will see if you go to grouped data, there's s squared, which you see I have written here. And then if you look at s, what do you see? You see this big, long formula, which is right. I mean, I typed it out. It's right. However, I tend to not want to write the whole formula out again because, look, all you're doing, what it's doing is taking this and taking the square root. That's why I said just take your answer here, take s squared, which is this, and take the square root to get the standard deviation. Okay? So basically, you calculate the variance, sample variance, take the square root of that, and you get sample standard deviation. Now, population variance has a Greek symbol. Now, usually your population parameters do have Greek symbols. That's a lowercase sigma. So that is an uppercase sigma. That's a lowercase sigma. So the population variance has the formula sigma squared. It's a big fraction again. And it's almost the exact same formula. It's the sum of the m squared times f's minus the sum of the mf's squared, except because you're dealing with population data, you divide by n. And here's the biggest difference. You only divide by n, not n minus 1. Okay? So population variance, we have the same basic numerator, but the denominator is a plain capital N instead of n minus 1. But here's the nice thing. If you want to calculate standard deviation, the standard deviation for a population has the formula, or has the symbol sigma, lowercase sigma. Well, if variance is sigma squared, but you want sigma, what do? You take the square root of sigma squared. So again, you get that answer. That's your population variance. Take the square root to get population standard deviation. Okay? So these are all our grouped data formulas. What about ungrouped data? They're actually going to be very similar to these. I mean, not exactly the same, clearly, but they're going to look similar. The symbols are the same. S squared, S, sigma squared, sigma. So S squared, that's the sample variance. It's going to be a big fraction. On the bottom is n minus 1. On the top is the sum of the x squareds minus the sum of the x's squared over lowercase n. So that's the sample variance. And if you want the sample standard deviation, again, you do the exact same thing. Square root of s squared. Basically, take the square root of this answer. So you get that answer to your calculator, take the square root, gives you standard deviation of the sample. Well, population. Okay, population variance is sigma squared, big fraction. It's the sum of the x squareds minus the sum of the x's squared over capital N over capital N. So notice it is reminiscent of the grouped population variance formula. By the way, really make sure not to mix these things up. If you mix these things up, you'll get the wrong answer. It's just remember that says you square all the x values first, then add. This says you add all the x values first, then square. It's not the same answer. We found that to be true in Chapter 1. You don't get the same thing. Now, population standard deviation has the formula sigma, just like over here. And all you have to do is take the square root of your population variance. So, get this answer, take the square root. That's how you get population standard deviation. Okay? All right, let's use some of these formulas. So far we haven't done any of these calculations, and we haven't done any grouped calculations yet. So we're going to do grouped calculations in just a minute. So let's do an ungrouped calculation first. And let's see what our data say. It says the data below give the salaries in thousands of dollars of all 6 employees at a small company. Calculate the range, variance, and standard deviation. It is very important that before we even talk about formulas, that we figure out if this is sample data or population data, because that changes how we calculate those things. Range actually doesn't make a difference, but as far as variance and standard deviation, if you accidentally use population formulas when you should have used sample formulas, you will end up with the wrong answer. So you have to be careful. Now let's see. How do we know if it's population or standard? Population or sample. The data below give the salaries of all 6 employees at a small company. This is everybody. This is the salary of everybody at the company, population data. If it had instead said the data below give the salaries of 7 employees from a very large company, well then you would assume it's sample data, because if it's 7 from a very large company, well then that's not everybody, so that's sample data. But here it's all 6 employees at a small company, so that's population data. By the way, it's ungrouped. It's just a list of numbers, which is ungrouped data. So we are ungrouped data, population data. So we're going to be working with these formulas. Very important that you choose the correct ones. Otherwise, you'll get the wrong answers. You have to choose the right ones. Okay, so let's see. I guess let's do the range first, since that's the easiest. Range is just the highest minus the greatest minus the least. So let's see. What's the biggest value? 108.4. Minus smallest value, 52.5. So the range is 55.9. Okay, easy enough. Now, standard deviation and variance take a little more work. We have to do the variance first. You have to do the variance before you can get standard deviation. So let's just hop right in. Sigma squared is the variance. It's a big fraction. Now what we need is the sum of the x squareds, and we need the sum of the x's. We already know n. N is 6 employees, so a 6 is going to go right there. And a 6 is going to go right there. That's where n goes. But we need the sum of the x's and the sum of the x's x squareds. So let's see, just off to the side somewhere, maybe over here, sum of the x's and sum of the x squareds. And let's see what we end up getting. So 88.5 plus 108.4 plus 65.5 plus 52.5 plus 79.8 plus 54.6. Let me double check all these numbers. 54.6. 79.8, 52.5, 65.5, 108.4, 88.5, yeah, we're good, so that's the sum of the x's. 449.3. And now we need the sum of the x squareds. So that's 88.5 squared plus 108.4 squared plus 65.5 squared plus 52.5 squared plus 79.8 squared plus 54.6 squared. Okay, bigger number, but we'll see how it works out. 35,978. Don't round these numbers. You want to hold off on rounding as much as you possibly can until the very end. You get into a lot of trouble if you start rounding in the middle of a calculation. You want to always hold off, if at all possible, till the very end. So we have the sum of the x squareds and sum of the x's. So, plugging into our formula, well, the sum of the x squareds go top left. So 35,000 goes here, 35,978.51. The sum of the x is 449.3 squared goes there. And now this is just a job for your calculator. So let's see. What I would do, I'd probably just put some parentheses, 35,978.51 minus 449.3 squared. You don't need parentheses there. It's just squaring that one value. 449.3. They're necessary in the formula, but once you have that number, you don't have to use parentheses. Divide by 6. And the calculator knows do the exponent first, then do division, so that's fine. Now that's the entire numerator typed out. Divide by 6. And there you go. Now, here's where you got to be careful, like I said, about rounding. So here is sigma squared. So I'm going to go ahead and round this to say, I don't know, 4 places. 9047. So let's say you're doing homework, and this could be an exact homework problem. Calculate range, done. Calculate variance, done. But now you want to be careful when calculating standard deviation, because you don't want to use this rounded number to calculate standard deviation. You want to use that, well, that's technically rounded, but you want to use that with all those decimal places intact, because you don't, if you're rounding standard deviation to 4 places, you don't want to take the square root of a number round to 4 places. You want to take the original number and square root that. So again, all you have to do is take the square root of your answer, but again, use the unrounded version. So like 388.9047222. Here's a little trick for you. And most calculators will do this. If you, so hit square root, and then if you hit second negative sign, it'll say A and S for answer. That's going to input the previous answer from the previous line. So that way you don't have to retype it. There you go. So the standard deviation is 19. And now I'll round this to 4 places. 7207. 7207. Of course, always make sure to round how directions indicate to round. Okay. Always make sure to round appropriately. So there is our standard deviation, population standard deviation, that is. Here is our population variance. And of course, there's our range. Okay? So you have to make sure to calculate, or first of all, use the correct formulas, calculate the sum of the x's, sum of x squareds, and plug in correctly. Let's see. Do we have time? Sure, we have a few minutes. I'll show you how to use your calculator to do this automatically. Okay? I have a YouTube video already that shows you how to do this, but I figured what the heck, it's a small data set. If you want to do this if you have a graphing calculator, or some scientific calculators will do this, you want to enter these numbers in a list. Now, on a graphing calculator, to access your lists, you hit Stat, on a TI calculator at least. And the first option you're going to be hovered on is Edit. Hit Enter. You're going to see a bunch of lists. If you've never used your lists before, yours will probably be empty. I'm going to clear mine all. So yours are probably going to be looking like this. And so just type the numbers in L1, list 1. So 88.5, hit Enter. 108.4, hit Enter. 65.5, hit Enter. 52.5, hit Enter. 79.8, Enter. And 54.6, Enter. Double check your numbers. 54.6, 79.8, 52.5, 65.5, 108.4. Oh, and I did make a mistake there. 88.5. Now, once you have those typed in, hit second mode to quit. Then all you have to do is go to Stats. Stat menu right there. Calc. And the first option is 1var stats. Click 1var stats. And if you have a TI-83, here I'll show you real fast. If you have a TI-83, it's the exact same process. So type in your numbers. Here, I'm in list 3 here because list 1 is being used by another program. So let's see. Let me type them in real fast. 88.5, 108.4, 65.5, 52.5, 79.8, and 54.6. Okay, same numbers. Quit, stat. If you have a TI-83, when you hit 1var stats, it doesn't do much. It just says 1var stats. But you have to do the same thing in both. Tell the calculator where your list, what list you're using. Here, I guess the last list I used in this calculator was list 3. I don't want list 3, I need list 1. That's where my data are. So I need to hit, if you go to see your keypad, has L1, L2, L3 in blue. That means hit the second key in 1, and that types in L1. Now on the 83, same thing except they're in orange, and I put mine in L3. So hit second L3 to tell the calculator where your data are. Regardless, if I typed in the numbers, hit enter on both of those, or hit calculate for the 84, and notice, yeah, there we go, same information. Now what are we looking for? Notice we get x bar. We didn't calculate x bar for these data, but you get x bar. There's the sum of x's. That's we calculated that. Sum of x squared, we calculated that. And notice it says Sx and sigma x. Okay, you gotta understand what the calculator is saying. The calculator is saying S and sigma, but the calculator doesn't know if it's population or sample data, so it's giving you both. So we were actually doing population data, and notice that is our standard deviation. This would be the standard deviation if it were sample data, but we were working with population data. Remember, that's context specific. It had nothing to do with the numbers. It was all about the instructions and the context. So if we had been working with sample data, that would be our answer. Since we're working with population data, there's our answer. Okay? Notice the variance is not given. But if you want to find the variance, what you have to do is just take your standard deviation and square it. That is, if here, like the calculator just gave us that answer. Square it to get that answer. Okay? It also gives you the max and the min, some quartiles and stuff. Now, do be careful. I believe I haven't tried this lately, but I believe the calculator calculates quartiles differently than we do in our textbook. There's like a dozen ways to calculate quartiles and percentiles, and I believe the calculator is different, but I don't recall for sure. I should probably check that sometimes. So if you want to use your calculator to think about quartiles, double check it using our formula, because I'm not sure they yield the same answer. There's a lot of different ways to calculate percentiles, and they might not be the same way. But the way homework and test questions can be graded is using the formula that we used earlier today that's out of our book. All right, what about grouped data? So here we have grouped data now, and we want to calculate the mean, variance, and standard deviation. So let's think about our formulas here. Since they're on the previous page, I'll just jot them down for us real fast. The mean of a group data set is calculated. Oh, by the way, is this sample or population? The following data give the average commute time in minutes for 25 employees at a large company. So what do you suppose? Do you think 25 employees is everybody if they work at a large company? I'd say no. That okay, 25 employees out of a large company probably has thousands of people. So 25 people would be a sample. So this is sample data. Really important that first thing we ask ourselves is population or sample data. Here we're doing sample data. Okay? So let's see. That means our formulas is going to be x bar for the mean, and that was the sum of the mf's over n, like so. Then we had s squared for variance. It is a big fraction. It's the sum of the m squared f's minus the sum of the mf's squared over n minus 1. And of course, once we have variance, to get standard deviation, simply take the square root of that answer. Now, notice I made all these blank columns over here because that'll help us stay organized whenever we're calculating the sum of the m squared f's and the sum of the mf's. And you don't have to use this if you don't want to. It just helps us stay organized is all. Remember midpoints is when you take these two, they're called class limits, recall. 0 and 10 are the limits, lower limit, upper limit, lower limit, upper limit. You add them and divide by 2. So I mean, that's really easy. 0 plus 10 over 2 is 5. 10 plus 20 is 30 over 2 is 15. 20 plus 30 is 50 over 2 is 25. Notice they're increasing by 10 each time. 30 plus 40 is 70. Divided by 2 is 35. Again, difference of 10s. The next one's going to be 45. Those are your midpoints. And then MFs, well, that's when you multiply M's and F's, the pairs. So 4 times 5, that's just 20. Okay. 9 times 15, I don't remember exactly. 9 times 15, 135. 6 times 25, well, 6 quarters is what, $1.50? 6 times 25, yeah, and then 4 times 35 would be what, 140, I think. 4 times 35, yeah, 140. Then 2 times 45 is 90. Now, why do we do that? Because we need the sum of the MFs. So the sum of the MFs is just that column added. So that's 5 plus 15 plus 135 plus 150 plus 140 plus 90. 535. Then we can do the same thing for the m squared f's. So that means take each m, square it, multiply by its corresponding f term. So 5 squared times 4. Oh, I'm not sure why I used a calculator for that. 15 squared is, well, it's 225 times 9, I'm not sure. 2025. 25 squared, 625 times 6, 3750. Again, I'm squaring the midpoint, then multiplying by the corresponding frequency. 35 squared, I have no idea, but times 4 ends up being 4,900. And then 45 squared times 2 ends up being 4050. So, if I add that column, that's the m squared f's sum now. Let's see what we get. 100 plus 2025 plus 3750 plus 4900 plus 4050, we get 14,825. Now, really, that should be enough for everything we need. Of course, n is 25 is the sample size. So those 3 values are enough to calculate the mean, the variance, the standard deviation. So let's see. X bar, that's the sum of the MFs, which are 535 over n, 25. And then we just use a calculator. 535 over 25, 21.4. So that's the average commute time of that grouped data set, 21.4 minutes. Okay. Then we're going to have, let's see, variance. So we need to use this formula. So s squared is a big fraction. It's the sum of the m squared f's, 14,825, minus the sum of the mf's, 535, squared divided by sample size, which was 25, divided by sample size minus 1. 24, basically. Let's go ahead and write 24. Divided by 24. Equals, let's see here. Again, put parentheses around your numerator. 14,825 minus 535 squared divided by 25. Close your parentheses. Again, the calculator knows square, get that answer, then divide, then subtract, because the calculator certainly knows the order of operations. Then divide by 24. $140.6, I'll just say point, well, we need to round it, I guess. So let's round to 4 places and say 0.6667. But remember, the next thing we want to do is calculate standard deviation. And standard deviation, S, is the square root, then, of 140. I'm going to say 0.6 repeating because I don't want to use this rounded version when I calculate the sample, the sample standard deviation. I want to calculate using the unrounded version. So again, do the square root and hit second negative sign to type in the answer from the previous line, the unrounded version, and there we go. It's 11. Now I can round this to 4 places. 8, 6, 0, 3. You know, sometimes it'll make no difference at all. You'll get the exact same answer if you use the rounded version, but sometimes you won't, and it's better to be safe than sorry. By the way, standard deviation is always in the original units, the units of the original data. Variance is in minutes squared, which really doesn't have, any good practical interpretation. But, that is certainly the answer. But that's why we prefer standard deviation, because of the, we have a practical interpretation of minutes matching up to the original units instead of minutes squared, whatever the heck that means. Okay, so that's grouped quantitative data. Again, these were sample data, so we used the sample formulas from the previous pages, and then it was just making sure we typed into our calculator correctly. Okay. Now, what can we do with all these things? Standard deviations. We're going to use standard deviation. Last page, finally. It's been a long lecture. We're going to use standard deviation a lot. Before we get to section 8 here, I want to talk about how you compare standard deviations. Okay, let me flip back to the previous page real fast. We've calculated 2 standard deviations. We have calculated this one, and we have calculated this one. However, you can't just say this standard deviation. Okay, let me back up in just a minute. Standard deviation is a measure of variability. It tells you how far apart your data are spread out from the mean on average. That's what standard deviation does. So, in general, we would say a bigger standard deviation means the data are more spread out. A smaller standard deviation means the data are closer together. However, when you're comparing these 2 standard deviations from different data sets, you can't just say, well, 19 is clearly a bigger number than 11, so that means this data set is more spread out. It's more variable than this data set because that one has the bigger standard deviation. You can't say that because they're in different units. They're different. The underlying data are completely different. Okay? Basically, these numbers are pretty big, so you expect a bigger standard deviation. These numbers are on the smaller side, numbers from 10 to 50 are on the smaller side. You expect a smaller standard deviation. So you can't just look at the nominal numbers and say 19's bigger, so that data set is more spread out. Okay? What you can do, if you want to compare two standard deviations, what you have to do is calculate what's called the coefficient of variation. It's a very easy formula. Basically, all it does is it compares the standard deviation to the mean. It's a ratio of the standard deviation to the mean. So what is the coefficient of variation? It's a measure of relative variability. We use it to compare two or more standard deviations. So if you want to figure out which standard deviation represents greater variability, you have to calculate the coefficient of variation for each. Then you can compare the coefficients of variation. So for a sample, again, super easy formula. We say CV for coefficient of variation. It's going to be S divided by X bar times 100 and then percent. The coefficient of variation, if you have population data, all we're doing here is changing the symbols out for population. It would be sigma over mu times 100%. You're doing the exact same thing both times. You're taking the standard deviation, dividing by the mean, multiplying by 100%. Okay, so if we want to compare the two previous standard deviations, we have to take the standard deviation, divide by its mean, times 100, then we can compare the two coefficients of variation to figure out which one has greater variability. Then you can just compare, you're comparing apples to apples. You can say the bigger one represents more variability. So let's see. The second one, okay, we had a standard deviation of 11.8603, and we had a mean of 21.4. So let's jot that down. Here, I'll do it on the right-hand side. That was the second one. So this was the commute times data set. Commute times. It had an X bar of 21.4, and it had a standard deviation of 11.8603. So the coefficient of variation is going to be the standard deviation, 11.8603, divided by the mean, 21.4, times 100, and then make it a percent. So the coefficient of variation is what? 11.8603 divided by 21.4 times 100. So we could say about 55.4%. So there's the coefficient of variation for the commute times data set. Now the other data set was what? I think it was salaries. We'll just say salary data set. Okay. Salary data set. Okay. It had a what? It had a standard deviation of 19.7207. So sigma was 19.7207. You know what? For this one, we didn't calculate the mean because it wasn't asked. Oh, you know what we did? We did with our calculator, though. So we can pull that back up. I still have that data saved in that list. So it's off the screen now, but I still have those data in list 1. So I can just go back and, so quit that, go back, hit stat, go back to calc, hit 1var stats again, and it still has list 1 saved there. Scroll down, hit calculate, and there it is. The mean 74 point, let's say 74 point, just 88 is fine. So the mean, mu, is 74.88. By the way, notice it says x bar, but remember there's no practical difference in the formula for x bar minus mu. So the calculator says x bar, but mu is calculated the same way. Because this is population data, so we do need a mu, but mu and x bar have the same formula, so that's fine. All right, so to calculate the coefficient of variation now, it's the standard deviation, 19.7207, divided by the mean, 74.88, times 100, make it into a percent, and so we get that the CV is what? The coefficient of variation, 19.7207 divided by 74.88 times 100 is about 26.3%. So what's the moral of this story? Now we can say we're comparing apples to apples. Which one of these has the bigger coefficient of variation? The one with the bigger coefficient of variation, that is the data set with greater variability. So it actually turns out that this one has greater variability. That is, that standard deviation represents a greater variability than that standard deviation does, even though that number is bigger. What you have to realize is basically that number is bigger because the numbers you're working with are bigger. Here we were working with smaller numbers, so we expect the standard deviation to be smaller. But this standard deviation is bigger compared to the mean. So 11.8 is bigger compared to 21.4 than 19 is compared to 74. So even though it's a smaller number, basically the data here are more spread out. The commute time data set is more spread out compared to the salary data set. But you have to calculate the coefficient of variation before you can make that determination. All right, last thing to talk about. 2 ways to use the standard deviation. We're going to actually, throughout the class, use a whole bunch of different ways. But 2 ways right now, we're going to use something called Chebychev's theorem and the empirical rule. Chebychev's theorem gives basically the lower bound of the percent of data that should fall between 2 points that are equidistant from the mean. The important thing about Chebychev's theorem is that it works for any distribution, whether the distribution is bell-shaped, whether it's skewed, whatever. It works for any distribution. It's a really important result. And here's what we mean when we say the percent of data that falls between 2 points equidistant from the mean. What we mean by that here, I got a new little toy. Hopefully this will help. So there's a distribution. That's a bell-shaped distribution. Now, Chebychev's theorem does not have to have a bell-shaped distribution, but that's bell-shaped. Okay? The mean is right in the middle here. What we mean by 2 points equidistant is like if you look to the left, let's say, a standard deviation is just a number. So if we go 1 standard deviation, 2 standard deviations, if we look, so there would be, let's say, that's mu plus sigma, and that's mu plus 2 sigma. That's 2 standard deviations above. And if you look at mu minus sigma, that's 1 standard deviation to the left, and another mu minus sigma, so mu minus 2 sigma. So if you look at 2 points equidistant from the mean, and you look at all the data between those points, Chebychev's theorem is going to tell you at least what percent of data has to be shaded there. So look to the left, a certain number of standard deviations, look to the right, a certain number of standard deviations, and Chebychev's theorem says how much data should you expect there at least. It's just a formula. The formula is this: 1 minus 1 over k squared percent. So do this little formula where k is the number of standard deviations. So here, this picture is for 2 standard deviations. If you want to know what percent of data should be shaded there at least, well, plug in a 2 into that formula. Well, that's easy to do, right? If you plug in a 2 into that formula, you get 2 squared is 4. So that's 1/4. 1 minus 1/4 is 3/4. Well, what percent is 3/4? 75%. Again, you don't have to do it in your head, but okay, if you plug in 1 minus 1 divided by 2 squared, that's 75%. If you turn it into a percent. Okay, what about for 3 standard deviations? Okay, so you probably can't do 3 in your head. I mean, you can do the fraction. If you plug in a 3, it's 1 minus 1 over 3 squared, so it's 1 minus 1/9. Well, 1 minus 1/9 is 8/9. So whatever the decimal of 8/9 is, I don't know. But 1 minus 1 divided by 3 squared is that. Turn to a percent, so 88.9%. You know, you can do any k. I should specify up here. K, I need to add that, is bigger than 1. So k has to be bigger than 1, but as long as k is bigger than 1, you can plug in any value you would like. Like you can plug in 2.5 standard deviations. You know, just into your calculator. You know, here I'll do another bullet real fast. At least some percent of the data fall within, let's say, 4.5 standard deviations of the mean. You can plug in 4.5 into the formula. So 1 minus 1 divided by 4.5 squared looks like 95%, basically. If you round that to, if you turn it to a percent and then round to 1 decimal place, it'd be 95.1%. So 95.1%. All you have to do is plug into the formula. Okay? That's Chebychev's theorem. But remember, Chebychev's theorem works for any distribution. So your distribution might be skewed. What kind of skewness is that? Skewed to the right. Or your distribution might be like all kind of crazy, like something like this. It doesn't matter. Your distribution could be nice and bell-shaped, but it doesn't have to be. That's the beauty of Chebychev's theorem. Now, the empirical rule is the last thing, and then we'll do some examples of these. The empirical rule gives the approximate percent of data that fall between 2 points equidistant from the mean, but the catch is it only works with bell-shaped distributions. So it only works when you have a nice bell-shaped distribution. I need some more ink, like that. So that's what's called a normal distribution, a bell-shaped distribution. It's a nice symmetric curve. The empirical rule only works when you have a distribution like this. So what does the empirical rule say? It says, okay, the mean is right in the middle. If you have a normal distribution, the mean is the value right in the middle. If you look 1 standard deviation to the right and 1 standard deviation to the left, so that would be mu minus sigma, and that would be mu plus sigma. If you shade these data, the empirical rule says that's about 68%. If you look 2 standard deviations instead, so go one further. So if you look at mu plus 2 sigma, or that value would be mu minus 2 sigma. So if instead you went 2 standard deviations above and below, and so you shaded like this, that much, well, the empirical rule says 95% approximately should be shaded. And then the empirical rule says if you go 3 standard deviations out. Now, 3 standard deviations is right there. That's mu plus 3 sigma, and there will be 3 standard deviations to the left, mu minus 3 sigma. Now, you might say to yourself, well, now you've gone and shaded the entire thing. Well, not exactly. Because what I can't show here whenever I use this stamp or I draw a normal distribution is, if you zoomed in right here, the curve actually goes on forever to the left and right. So even though we only draw it, obviously we don't draw it forever to the left and right. You can't draw forever to the left and forever to the right. We have to cut it off somewhere. But the curve goes forever in both directions. So there's a tiny bit over here to the left I haven't shaded, and a tiny bit over here to the right I haven't shaded. What the empirical rule says, though, is you've shaded about 99.7%. If you look 3 standard deviations to the left and to the right, you're going to have approximately 99.7% of the data. Okay? I don't know why I can't get that 9 to work. Here, let me break that. 99.7. Okay? That's the empirical rule. Now, what's the whole point of this? Why do we even do the empirical rule? Let's look at a couple examples. Okay? The test scores on a recent stats test were skewed to the left with a mean of 75 and a standard deviation of 10. Determine at least what percentage of students scored between a 55 and 95. Okay? So for a problem like this, draw a picture. Draw a picture. It says the data were skewed to the left. So that looks about something like that, maybe. Skewed to the left. You have a long tail on the left side. Here, I'll make it more pronounced. Something like this. Longer tail on the left side. Okay? So the mean was a 75, so 75 is like right there somewhere. Now, we want to know what percentage of students score between a 55 and a 95. Okay, well, 95 is like over here somewhere. 55 is over here somewhere. And the question is, how many standard deviations does it take to get from 75 to 95? Or from 55 to 75? It is like, what's this distance? Or what's this distance in terms of the standard deviation? Well, the standard deviation is 10. So think about it. To get from 75 to 95, you add 10. So there would be 1 sigma. And if you add 10 again, you get 75, 85, 95. So you're talking about sigma is 2 standard deviations. That's k. Oh, sorry, no, I said that wrong. Sigma is 10, but k is 2 because you're talking about this distance here, k, is 2 standard deviations. And notice to get from 55 to 75, again, what you do is you add 10 to get 65, then add 10 again to get 75. So that distance is a distance of 2 standard deviations, so k is 2. Well, if k is 2, just according to Chebychev's theorem, 75% of the data at least has to be shaded like so. So all you have to do there is find the correct value of k. Now, a common mistake here is to say 4 standard deviations because it's a span of 10 plus 10 plus 10 plus 10 to get from 55 to 95. But you're not talking about the whole distance. You're talking about the distance from the mean to either the greatest value or the lowest value. Okay? So that's how one way we're going to use Chebychev's theorem. Basically, figure out the value of k. If it's 2 or 3, well, there's your answers. If it's like 4, 5, or 6, well, then all you have to do is plug in to the formula. Now, let's see. If the data example 8.1 were known to be normal, okay, if you know the data were normal, well, then you can use the empirical rule. So the empirical rule means, we have a nice bell-shaped distribution, okay, where 75 is in the middle, and then you have 95 and 55. But again, we don't really have to even really draw a new picture because all we need to know is what's that distance. But the distance is still the same. It's 2 standard deviations. That distance right here is, we'll say, 2 sigma. It's 2 standard deviations. And what does the empirical rule say about, 2 standard deviations? And if you're looking at all the data in between, 95% of the data has to be between. Okay? Now, 8.3 changes it up slightly. And basically, it adds one additional step. A data set consisting of 500 Wechsler IQ test scores. That's like just the regular old IQ test score, the main one. So a data set consisting of 500 Wechsler IQ test scores is normally distributed with a mean of 100 and a standard deviation of 15. Approximately how many scores fall between a score of 55 and a score of 145? Okay, so we know we have a bell-shaped distribution again. So something like this. Okay, where the mean is 100, and we want to know how many scores fall between 145 and 55. So the first step is the same. How many standard deviations does it take to get from 55 to 100 or from 100 to 15? It should be the same answer either way. Well, let's see. If sigma is 15, standard deviation is 15. So basically you're asking yourself, how many times do I have to add 15 to go from 100 to 145 or to go from 55 to 100? And I think the answer is going to be, 3 of them, right? Because this distance right here is 15 plus 15 plus 15 is 45. It's 3 sigma, which is the same as this distance. Again, 55, if you add 15, then add 15, then add 15, you get 100. So that distance, again, is 3 sigma. So here, we're talking about k equals 3, but I guess I shouldn't say k equals 3 because we're not talking about Chebychev's theorem, because we know it's normal. If a distribution's normal, then we can use the empirical rule. Now, the empirical rule says that 99.7% has to be within 3 standard deviations. So if I shade all of this, this has to be 99.7%. However, that's not what the question asked. The question asked, how many scores? So be careful with this. We know that has to be 99.7%, but of 500, that's going to be how many scores. We need to find 99.7% of 500. So let's see. 500, now to multiply by a percent, you put it in decimal form before you multiply. So times 0.997. Of course, I probably need to round this to the nearest whole number, 499. If we round to the nearest whole number. Okay? So be careful when it's asking, if I ask you a test question or a homework or quiz question, if I ask for a percent, well then you're done like the first two questions. But then if you ask for how many scores, well then you have to take whatever percentage you find of the given sample size. Now the last variation, so there's been this, the first two are kind of the standard applications. That's a kind of a variation. Now we have one more variation that you might see pop up on a homework or quiz. It says, suppose the data set in example 8.3 were not known to be normal. So the data is not normal. It's not bell-shaped. So it's skewed or something. So let's say it's skewed. Sorry, excuse me that. Okay, so at least 96% of the data test scores should lie between what two test scores? Okay, this is kind of like asking the question backwards. Okay, it says the data are not normal. Not normal. That means use Chebychev. Use Chebychev's formula. Okay, so use Chebychev's formula. Now, at least 96% of the data. Okay, so we have a mean of 100. We know that. And we know that sigma is 15. But this is like reversed the question. So instead of giving us two values and saying what percentage is between those values, this is asking the opposite. It's giving us a percentage and saying find the two scores that are like over here and over here. So question mark, question mark. Well, what you need to do is, I think, figure out what value for k do you plug in to Chebychev's formula, and it spits out 96%. Well, we know that if you plug in 2, you get 75. Plug in 3, you get 88.9. Now, let's see. Let's plug in 4. We're looking for what do you plug in and get a 96. So if you plug in 4, 1 minus 1 divided by 4 squared, you get 93.75. If you plug in 5, 1 minus 1 divided by 5 squared, oh, there you go. 5 standard deviations. So if you plug in a k value of 5 into Chebychev's formula, you get 96%. So that means if you want 96% of the scores to be between two scores, you need to look 5 standard deviations above, 5 standard deviations below. So by 5 standard deviations above, I mean you need to do 15 plus 15 plus 15 plus 15 5 times. In other words, 15 times 5, 75. So this value over here is going to be 175. And then you want to look 5 standard deviations to the left of the mean. Again, 5 standard deviations is 75 points. So 100 minus 75 would be 25. So that means that if for some reason, now of course we know that IQ test scores are normal, normally bell-shaped distributed. But if we did not know that, if we were assuming that the distribution was not normal, then we could say, according to Chebychev's theorem, though, that 96% of the scores should be between 25 and 175. At least. That's like a worst-case scenario. Between at least 96% of the scores should lie between a score of 25 and 175. Okay? So we had just your basic applications, or basically figure out how many standard deviations you're talking about. Don't try to find the entire distance in terms of the standard deviation. Find the distance from the mean to the upper value or the mean to the lower value in terms of the standard deviation. How many increments of 10, for instance, does it take to go from 75 to 95? 2 increments. So K was 2. Or like over here, example 8.3, it took 3 standard deviations. How many standard deviations does it take where the standard deviation is 15? So how many increments of 15 does it take to go from 100 to 145? Well, 15 plus 15 plus 15, 3 standard deviations. Okay, but the variation here was, well, we're not looking for the percentage answer. We're looking for how many scores, which is once you find the percentage, multiplied by the sample size of 500. Then the last variation was reverse engineering. If you're given a percent, reverse the problem. So if you're given 95%, reverse to find 55 and 95. Or if you're given 75%, reverse to find 55 and 95. And that's what we did exactly here. We reversed the problem. We figured out what value of K resulted in the formula for Chebychev's theorem giving us 96%. We found out that K was equal to 5. Well, we then said if K is 5 and the standard deviation is 15, well, 5 times 15, which is 75, if you look 75 units above and 75 units below, that'll give you the 2 scores that you're looking for. Okay? That wraps up Chapter 2. So, again, I hope you are sticking around to the very end. I know these lectures are long, but I mean, if we were in class, this would be a 3-class day lecture. So just treat this class just like you would be going to class 2 days a week. It would take us 3 days, a week and a half worth of class to finish Chapter 2. So, even though you're watching this online, make sure you're giving it its proper attention and, following along. Of course, if you're online, use YouTube to speed it up a little bit, a little faster. But just make sure that you're watching this, because this is giving you more or less the same experience of being in class, minus the ability to answer questions or to ask questions. Okay, that wraps up chapter 2, and we'll do Chapter 3 soon. If you have any questions, always feel free to post to the Ask Your Professor discussion board. That way we can have conversations there, have a nice equation editor, and we can all students can benefit from your questions and my answers. Okay, have a nice day. Talk to you soon.